Okay, let's talk about amplifiers built on op amps. We'll talk about the inverting, the non-inverting, and the difference amplifier. So we start with the inverting amplifier here, and the um, the idea here is we're going to talk about the ideal inverting amplifier first, and we can analyze this circuit using Kirchhoff's laws and Ohm's law. So we know, for example, that the voltage at this point here is 0, which means that the input current is equal to VI over RI. And we know that the output current, or the current flowing through R2, is equal to the current flowing through R1. And then with Ohm's law, well, we used ohms to get I1. We can use Ohm's law with I2 to get VO. VO is then equal to 0 minus I2 times R2, 0 being the voltage at the left-hand side of R2. And when we put these together, we get VO is equal to minus R2 over R1 times VI like this. Okay, so that's the gain. For the input resistance, the way we figure the input resistance is that we attach a voltage source, figure out what the current is, and then the input resistance is the ratio of those two. So we attach a source VI on the input. We already did that, but let's work through it again. And then we figure out what is the current. Well, the current is equal to VI over R1, and then the input resistance is then equal to VI over II, which in this case here is equal to R1. So this amplifier has an input resistance, R1. So in this case here, we have assumed that the amplifier has infinite gain, okay? And that allows us to assume that the voltage at the inverting node is 0. Now let's look at the case when the amplifier does not have infinite gain. In that case, and here's some equations, in that case here, we write this equation down. The output voltage is equal to the difference between the two input nodes multiplied by the gain of the amplifier. And of course, this equation also holds for the ideal op amp with infinite gain. That's how we get that V plus and V minus must be equal, okay? Now with V plus being equal to 0, we can convert that equation into this. So the voltage at the inverting amplifier input is minus VO over A, okay? Then we can compute the input current, right? And I have that here. I can write it again. I is equal to VI minus V minus divided by R1, right? The voltage drop across that resistor R1 divided by its value, that's the current, okay? And that ends up looking like this here. Minus V minus is VO over A. Then I can compute the output voltage, and I'm proceeding the same way that as I did before. I can compute the output voltage, which is the voltage on the left-hand side of resistor R2 minus I2 times R2. That's what I have here, okay? And I plug in what I know, V minus is equal to minus VO over A, and I have I1 from right above, and then multiplied by R2. So now I have this equation that relates VO, which is here, here, and here, with VI, which is here. And now I just need to rearrange that equation in order to get the relationship between VO and VI, and we do that on the next page, okay? Here's that same equation. I have VO here, and here, and here, and I have VI here, and I rearrange that equation to get the equation down below here. Okay, now this equation has two pieces. It has the piece minus R1, sorry, minus R2 over R1, which is the ratio that you're familiar with. And then it has another piece, which is 1 over the thing in the square bracket. So that 1 over the thing in the square bracket, that second term, or second factor, it is a result of the non-ideal gain of the amplifier. Now, as long as 1 plus R2 over R1 is much less than A, then that square bracket is equal to 1. And the equation reduces more or less to the one that we're familiar with, which is that VO over VI is equal to minus R2 over R1. But what happens when 1 plus R2 over R1 is much greater than A? Well, in that case, if 1 plus R2 over R1 is much greater than A, then in the square bracket here, we end up eliminating that 1. And then the equation transforms into this equation here, where it's minus R2 over R1 divided by 1 plus R2 over R1 multiplied by A. And R2 over R1 is much greater than A, which means that we can eliminate the 1 down here, and then the two other terms cancel out, and we're essentially left with A. Well, actually, it's a minus A, and you should have that little correction here. We're essentially left with a minus A. Okay, so that means that the gain can on this amplifier can go up to the open loop gain of the op amp, but not any higher. Okay, and if you really want to be operating this well, you need to make sure that the gain on your amplifier is much less than the open loop gain on the op amp. Here's a non-inverting amplifier, and we're also familiar with it. It looks very similar to the inverting amplifier, except that we swap around the voltage source. We move it from over here to over here, and we move the ground back there. Okay, we can go and analyze this as well. This point, the inverting point right here, that is equal to VI, and we can work through our calculations again, and we end up with VO over VI is equal to 1 plus R2 over R1, like that. Okay, now the input resistance of this amplifier is different from the input resistance of the inverting amplifier, because the source is attached. The source is attached right here. What's the current flowing? What's the input current here? I. Well, it's equal to 0, right? Because no current flows into an amplifier. So we have then, we apply a VI, we get a II, which is equal to 0, and then the input resistance, it's equal to VI over II, which is equal to infinity. Okay, so it has infinite input impedance, does the non-inverting amplifier, and that's an advantage of that type of amplifier. Okay, we want to look at one more type of amplifier before we finish off here. That's what's called the difference amplifier. And so the two previous amplifiers, they take a single voltage and they amplify that voltage relative to ground. The difference amplifier, on the other hand, it takes two voltages and it takes the difference between them and outputs a voltage relative to ground, which is the difference of those two multiplied by a gain. And I should break that down. VO is equal to some gain times VI1 minus VI2. Actually, I think in this case here, it might be VI2 minus VI1. If I want to make G, the gain positive, like that. Okay, so how do we work this out? There's two voltages. We can go through and do a very careful analysis of this, but perhaps what makes more sense is to use superposition. In superposition, we turn on one source at a time. So let's start by turning on VI2. Okay. So and then leaving VI1 off. That means that the point VI1 here is connected to ground. In that case, we have effectively a non-inverting amplifier, except that we have a voltage divider on the input. So the voltage that's seen on the input right here is actually a voltage division between R3 and R4. But then other than that, it gets multiplied by the gain that comes out of a non-inverting amplifier with R2 and R1. So that's what we have over here on the first part. We have the voltage V plus, well, actually, that's VI2 now, right? The voltage VI2 divided between R4 and R3, and then multiplied by the gain, okay? So that's that term. Now let's look at the other input, VI1, which in the equations here, I call V minus. That looks right here. We connect VI2 to ground. We apply a voltage, V minus, on input number 1, VI1. And when VI2 is connected to ground, the positive terminal is effectively connected to ground. And we have an inverting amplifier, and we end up with this expression over here. Okay. Now, in order for that to be a difference amplifier, we would want this gain here to be equal to this gain here. And that's what we write in this second line here. We say that gain must be equal to R2 over R1. And then we can work out what that means. Well, what that means is that R4 must be equal to R2. So that means this must be equal to this here. And it means that R3 must be equal to R1. R3 must be equal to R1 like that. Okay. Now, it's actually the ratios that need to be equal. Okay. But usually what you do when you build a difference amplifier is that you make them equal. You make R2 equal to R4, you make R1 equal to R3. Now, what about the input resistances here? Well, the two terminals have different input resistances. The input resistance is the effective resistance to ground. So we look at the input resistance of the positive side right here. And that input resistance is R3 plus R4. So I can write R in plus is equal to R3 plus R4 like that. If I go and look at the negative input, VI1 here, then Rn minus ends up being equal to R1, right? Because I connect VI2 to ground. That means that the negative input terminal is at ground potential as well, and then the input resistance is R1. So for the difference amplifier, not only are the input resistance is not really big, but they're also not equal. And that is a big disadvantage of the difference amplifier. And to solve that problem, we're going to look at another amplifier, which is called the instrumentation amplifier, but that is going to be in a different presentation. representation.